So now let's go ahead and talk about IX, which is this design for a high-performance network stack. So it's built on top of Linux. However, it's Linux with Dune, so the Dune kernel module. So it's built on the last paper. So we've got Dune here. And what happens is we are going to have a different API for networking. So we're not going to use the Linux API. Right? The Linux API, we go ahead and do reads and writes to sockets, which work like file descriptors. And so this is going to be a completely different both API and stack architecture. So we're just not going to be using the TCP/IP code in the Linux kernel. Instead, what happens is we've got on top of this an IX kernel. Right? And the IX kernel has its own TCP/IP stack. When we say stack, we just mean code for it, right? And then on top of that, we have our application. So our application can be multi-threaded. And what happens is then it talks to the TCP/IP stack, okay, with a call called run.io. This is a Dune process. So that we have the IX kernel running at CPL0 and the application running at CPL3. The IX kernel talks to the Linux kernel to do some things. How does it do that? It's going to be using a VM call. And I suppose we should really make this arrow go over into the Dune kernel, because it's the Dune kernel that's actually handling the VM call. And then also, below the Linux kernel, we have some hardware. A multi-queue NIC. A NIC is a network interface card. So it's just an Ethernet card. For Lab 9, for instance, you're working with an E100, E1000 NIC. And so the multi-queue NIC actually can provide multiple queues. So what we do is we actually talk directly from the IX kernel to the queue. And queue interacts with the NIC. Okay. These queues are actually in kernel memory in the IX. So that's where they're actually stored. So it's memory that is protected from the application. And so what is happening here is the TCP/IP stack is really doing two things with the queue. One, it's writing to transmit buffers. And the second thing is it's polling receive buffers. So this is the organization. Again, we have a multi-queue NIC. Currently, I'm just showing one queue. The queue is actually managed by the IX kernel, and the TCP/IP stack will write to transmit buffers to send packets, and it'll poll the receive buffers to receive packets. The packets will automatically be put in there by the NIC. And then there is a single API interface between the IX application and the TCP/IP stack here called run.io. So that's how we're going to actually be sending and receiving packets from the application itself. One thing to note is we're going to actually be able to support multiple queues. So we can have a second queue. We actually can support a second TCP/IP stack here And when I say 2, I really mean up to n. Right? In computer science, I think the word is there's 0, 1, or infinite. Right? And that's certainly the case here. So we can have any number of queues, any number of TCP/IP stacks here. And by these TCP/IP stacks, it's actually the same code. It's just different instantiations, so different values for its variables and stuff, and then different threads here. What's of interest is we're going to be dedicating a CPU to every thread and every TCP/IP stack, and we'll have a kernel thread associated with this too, which probably isn't going to matter too much. I guess I'll just show it down here. So this is a dedicated CPU. As well, thread 1 is running on its dedicated CPU, and thread 3 would be running in its dedicated CPU. This is how we're going to be getting high throughput and low latency. The cost is we're dedicating CPU. So CPL3, CPL0. Of course, these are running in, the Linux kernel is running in root mode. The Dune process is running in non-root mode. Right, this is just using standard Dune capabilities. The Linux kernel has to actually provide these dedicated queues that the NIC can use, right? Because normally the processes don't have access to the raw NIC. But here, the Linux kernel is privileging the IX process to be able to access these queues. Once that's done, Linux is involved not at all in the networking, right? It will still be involved in things like allocating memory, or if you have to read files or stuff like that, but it's totally not involved with the networking. The packet buffers, so this is interesting. When thread 1 actually wants to send a packet, it's going to go ahead and create, let's say not the packet, but some data that it wants to send, right? It wants to send, some data hello. It's going to pass a pointer to this memory along with a length. That's going to go to the TCP/IP stack here. We're not going to make a copy of this. Instead, we're going to, in this queue here, the queue actually saves addresses and lengths, and we're going to, in the queue, put a reference to this address and this length directly. So we're directly going to be sending out to the NIC. That is, the network interface card is going to be reading directly from application memory. This is called zero copy. And as you can imagine, copying memory, I mean, it seems like a mem copy, a mem move, how slow can that be? But it actually, comparatively, can be fairly slow. And so by not copying this at all, we are going to be saving time. The second thing we're going to do is when we have an incoming packet, again, we are not going to copy it into the user's address space, into this address space. Instead, what we'll do is we will provide, by manipulating page tables, we'll go ahead and provide a read-only access to the data of the packet that was read in. The packet buffers are going to be in shared memory between the IX kernel and the IX application. So we know if we have a small message to send, making a system call to send that message causes the system call overhead to be quite large. So if we have available 1 million system calls per second, and we want to be sending some XX million packets per second, then that really says that we need to be having multiple packets per system call. And that's exactly what we're going to do. Our run IO is not going to be just for a single packet. We're going to allow us to specify lots of different responses from this thread to send out. So we may send out hundreds of packets in a single run IO call. We may be reading in hundreds of packets that have been incoming. So let's go ahead and look at run IO. So run IO. We're going to pass in an argument, and it's going to contain one or more operations. So one of the operations we can provide is send to a TCP connection. So this would be an already established TCP connection, and we're saying send some data to it. We can do multiple of these. So we might have 100 or 1,000 TCP connections open, and we might send data to all of them in a single run IO. Another thing we can do is, if we're done with a receive buffer. I mentioned the zero copy, and the idea is that when the NIC gets an incoming packet, it's going to be put into memory. The TCP/IP is going to go ahead and figure out what TCP connection is that, where's the data from it, and then go ahead and through memory mapped IO make it available to the IX application. So once, and then the application runs. Okay, so the run IO gets called and it passes back the incoming packets. Well, now the application needs to use it, and only the application knows when it's actually done reading that data. So part of what we need to do here is tell the TCP/IP stack when we're done with the receive buffer that it has given us previously. What else can we do? We can close a connection. We can go ahead and connect to a remote server, or we can accept a connection if we're a server. Okay. So this is all the information that the application is providing to the TCP/IP stack in the IX kernel. That is, here's data to send over existing connections. Here's management of connections, like closing a connection, opening a connection, accepting an incoming connection, and giving back buffers, basically giving back buffers that have previously been provided. So that is what's going out on the run IO. What's coming in, so this is outgoing, and then we also have incoming. So incoming is on return from run IO. What is, just think of this as a big buffer that run IO, you pass into run IO, right? This big buffer with a lot of information in it. And when you come back, it has got new information in it. So this new information is going to be first the result of each of the outgoing operations. So each of these operations has a result. Clearly, done with a receive buffer, there's not much. I'm sure that just works. Sending to a TCP connection may or may not succeed. For example, the connection may have been closed. That's a result that may come back. It may have worked fine. That's okay. It may have only sent some of the data, so it'll return how much had been sent. It may have sent none of the data, in which case it'll return that too. Okay, and then what else are we going to get? We're going to get receive on a connection. So a connection now has some data that's available from it. So this is because of incoming packets. What else? We may have a connection opened or connection terminated. So this will tell us status about connection. So that'll all be coming back. And what happens now is each crossing from user to kernel, right? Each system call does a lot of work. So we're amortizing our system call cost against lots and lots of packets. So if we look kind of at how this thread is going to be structured, it's going to be something like this. So it's going to be, we'll just have this infinite loop while true, and we will, so we'll go ahead and run IO. Rather than the same buffer, we actually use different buffers. So we have the incoming and the outgoing. And then we'll go ahead, for every message that's in the incoming buffer, we're going to go ahead and process the message in some way. And then we're going to send a reply. So that is the basic structure of one of these threads. As you can see, we have lots and lots of messages that we may be both incoming handling and then outgoing appending. All right, so here is how we're going to be dealing with the application. So what's going to happen is we've got here a packet that comes in, right? It comes in and gets put into a buffer. There's a whole bunch of packets that are in here. TCP/IP then process it. We're going to be going ahead, and it looks like a copy, but it's not really a copy. So the application on doing a receive IO is going to be receiving all this data for all these different operations. The application uses a little library to be doing this, so it doesn't have to call run IO directly. It can have a slightly higher level interface. And then the application will then sit there and process these incoming packets, this data that's incoming. And in response to that is going to send out requests. It's not always going to be one for one, that there's incoming data and there's an outgoing response, but usually that's the case. And then it's going to batch this up and send those out in a single system call. So single system call reads in all this data, sends in all this data. Okay. So this is the response to the previous incoming packets, right? So in one step, we call receive IO, and the application sends out the response to the previous packets and reads new packets. In the next run IO, it sends out the response to those packets and reads in even more new packets. These go back into the TCP/IP stack. TCP/IP stack will then send them out properly. There's also a timer involved. The timer's there for things like the TCP/IP protocol has various timers, like it needs to send out some heartbeat packets. So if there's not been actual data that's sent on a TCP connection, it needs to send a keep alive packet. There are other sorts of timers as well. And then this goes back out to the NIC as outgoing packets. So the protocol and the application are all handled directly. What we're doing basically is we're running these packets to completion. We get an incoming packet, we go and we take it through the TCP/IP, we go ahead and it runs through the application, and then it goes back out. There's no queuing that has happened. So Linux uses CPU time moving packets through, there's these various stages and queues and so on. Okay, so that's good. If the application is doing something else, while it's waiting in a queue, there's other things that the application can do, but it's bad for network performance. There's locks, there's cache coherence and cache eviction, there's moving stuff from core to core, and the run to completion just says we complete the processing in one batch of inputs before we start on the next batch. And entirely complete. The NIC driver, the TCP, the application, all the way to getting the reply back out. And how do we do this? Because run IO is actually calling all the way out down to the driver. So what's happening actually is when you call run IO, that's when it goes and grabs the packets from the driver. So they're not coming in via interrupts. Instead, we're just going and reading them. Why do we do this? Well, this single thread carries these batches of packets. So this is a single CPU that's running. The single CPU calls run IO, and then we make the system call that goes into the IX kernel. The IX kernel will then go and both send out these, so through TCP and put them out in the outgoing queue, and then go and read whatever packets are there, process them through TCP/IP to get the incoming data. What do we avoid? Queuing, sleep wake up, context switch. The only context switch we have is this one system called a context switch here. Any core-to-core transfers, because this entire thing is happening in a single core. The packet are more likely to be kept in the CPU's cache, right? Because it's not that we have a huge number of them. We have only the numbers we're operating on. And so it's more likely that they'll be in the cache. And we don't have any problem balancing the processing rate. What if one part of this is slower? Let's say this part of the TCP/IP is slower. Well, that's going to just mean it's going to take longer for the run IO to finish, but it's not as though anything else is going to get ahead or behind. And we'll just have our entire throughput slowed down somewhat. Or if the application is slower, right? If the application is too slow, we might overflow our queue here, right? The NIC might overflow the queue. What happens then? Packets get dropped on the floor. What happens then? The other end of the TCP/IP connection is going to notice that there's no acknowledgement for their packet, and so they are going to slow down their response. So they're not going to send as much. So that's kind of a nice adaptive flow control in the sense of in regular Linux, what happens is packets just get coming in and there's interrupts and then copy and copy and copy and copy. We could have this huge glut of packets. And if we've got a slow application and a huge glut, there's nothing telling the other side of the connection, hey, slow down. This way, until the application is actually successfully handling them, we're not going to be allowing more packets to come in than will actually fit in this relatively small queue. So we are going to do polling instead of interrupt. Why? Interrupts are expensive. And also, if it's likely that there's data there if we were to go look, interrupts are sort of redundant. Okay, so for polling, we periodically check the NIC, the network interface controller, the DMA queue, right? DMA in the sense of we provided the NIC an address of physical memory, and it has as a queue, and it is going ahead and putting the incoming packets into that queue. When do we do this? On run IO. That's the time we do it. If you don't have something like this run IO case, it's hard to know when to check, right? The question is, where do you do that in a general case kernel? So if you check too often, you're wasting the CPU. If you're checking too rarely, you have the potential of overflowing the queue, and also the latency can be very high, right? You might have a packet that has come into the incoming queue and sits and sits and sits and waits and waits and waits until you actually go look. In our case, what we have is our application thread is, again, I'll just remind you what the code looks like in pseudocode, right? Again, what we do with this loop, we just call run IO with in and out. Out is the response to the previous data, incoming data, and in is the new incoming data. And then for every message in, we process it and output some sort of a reply. So run IO itself is going to do the polling. And it's okay, it's a dedicated core. So the downside of it is we may be wasting this core, but this core is going to be running sort of full speed. If there's no input, that is, if there's nothing in the queue, then there's nothing to be done. We'll just be calling run IO over and over and over again, and it'll be going and polling the queue. If we do have an input, it grabs a batch and returns to the application. It never waits. If there is nothing in the queue, it doesn't wait because there might be something in the queue. Run IO will go, find out what's in the queue, come back. If there's 3 packets in the queue, it'll deal with those. If there's 100 packets in the queue, it'll deal with those, and so on. So what's happening is at low load, we poll more often. Right? At low load, this processing, this for loop, is going to be quicker. At high load, this is going to be slower because we have more messages. Polling more often implies lower latency. At low load, we might be just going and calling run IO and getting an occasional packet, and we're going to pick up that occasional packet right away. And then we poll less often. We poll less often at high load, but we're automatically using larger batches, and that implies higher throughput. Our cost of this run IO system call is going to be amortized for these much larger batches. This is what the paper calls adaptive polling. But notice there's no constants that have to be tuned how to do it. It's just automatically. If we have low load, we poll more often. If we have a high load, we poll less often. The multi-core. So what about that? Often what's going to happen is one core can't give us enough throughput. For instance, if you have one core, you are going to still have most of a 10 gig Ethernet idle. Right? If you wanted to completely fill up a 10 gig Ethernet, you can't do it with one core. So we're going to take advantage of the fact that our server is dealing with lots and lots of clients. And they're all sending in requests. So they're all independent requests. So all these independent requests allow us to actually say, why don't we go ahead and have multiple cores dealing with these? So we're going to take a slice of the traffic conceptually here, let's say, and use core 1. And here, core 2. And here, core 3. And that way, assuming these are all independent, then we can just have each core do its thing. The problem is, if we have to deal with locking, as we've seen, that can be expensive, or moving data between cores, right? Having to use the MSI protocol and modify in one case, and then send messages, and then write to memory, and then read back from memory. That's expensive. So here's what we're going to do. We're going to just have, again, the NIC queue and the TCP/IP stack. So this is in the IX kernel. And the application thread. We're going to have all of these on a single core. And then we can go ahead and have another queue and another TCP/IP stack and another thread for the application on a separate core. And the same thing for multiple cores. And the idea is we shouldn't have to have any locking between these because they'll be completely independent. So we'll have, for instance, one connection here that as we are sending and receiving data on this connection, it's going through, let's say, Q1, going up through this TCP/IP stack, up through its thread, and so on. So there are timers in this TCP/IP stack. There are separate timers in this TCP/IP stack. By different stacks, I don't mean different code, right? It's the same code, but just different instantiation of it, different variables, for example. So we may have an area reserved for the TCP/IP stack 1 variables, another for the TCP/IP stack 2 variables, again, so they're not interfering with one another. So no data should be used on more than one core. For example, our packet content stays on a core. Our NIC queue stays on a core. Our packet free list stays on a core. The TCP data structures stays on the core. The app data stays on the core. And if we have that, we have no locking issues. We have no need to have any cache contention, or we have no need to copy memory from one core to another. It's not 100%, it's 99.9% true that there's no shared data. There's a little bit of shared data between those, and that is there is an ARP stack. So ARP is the address resolution protocol. That has to do with when we're sending out packets to various places, where do we actually want to send them on the network? What is the next IP address to be sending this to be routing it to? Okay. And that is, or kind of we think of as what interface to go to, what gateway, things like that. So that's a very small amount of data, and that is actually shared among these, and it uses an RCU locking for that. So reading is done without any locking at all. It's only updates that really happen very rarely that require a lock. One question is, what happens on incoming data though? So we've got below these queues a single NIC, right? It's a multi-queue NIC, so it has this capability. But how does an incoming packet know which queue to go to? An outgoing packet is very easy because the outgoing packets, this application is going to this TCP/IP stack is going to this queue. So that's how our outgoing ones are going. But incoming ones, how do we know? So we're going to do some mapping from an incoming packet to a queue. How are we going to do that? We're going to do some sort of, let's say, a hash based on, let's say, maybe the IP address and port, perhaps. And all that really matters is every packet for a particular connection needs to get sent to the same queue. It would certainly not be good if we have some connection and some of the packets are going to one queue and some of the packets are going to this other queue, which has never even seen that connection before. What we're going to do is basically have the Linux kernel set up these queues, set up the filters and the hashing to determine which incoming packets get sent to which queue. And then Linux is out of the picture, and it's just a matter of the IX kernel who is dealing with these incoming packets. So yeah, we're based on the sending IP address and the sending IP port. So those two then used as a consistent hash to decide which queue it goes to. This is sometimes called flow-consistent hashing, or, and I don't really understand the naming for this, receive-side scaling. I guess because of the fact that we are doing receiving and we're trying to scale, and it's happening on the receive side. So all of the packets for a given connection, TCP connection, go to the same core. That's good. We don't need to share the TCP state for a connection across the cores. The TCP state is for a particular connection, and so we can just deal with that. So there's a timer for a connection, and that will be stored within the stack that's handling that connection. There's no need to move the packet data to any other core because we're maintaining that complete state on this core. So when you call run IO, this thread is calling run IO, and it is looking at its queue. This thread is also calling run IO, right? It's running that same pseudocode that we looked at, calling run IO kind of as fast as it can, calling it, handling the incoming requests, and sending out responses, and then calling it again and calling it again and calling it again, and so on. It is dealing with its queue. So no contention between these, no shared memory, except that ARP that I talked about, but we're using RCU and that's not bad. And when a new connection comes in, that new connection again is going to be sent based on this hash again. Hopefully, the hashing results in a balanced load. If we're terribly unlucky, Q1 could be completely full and Q2 empty, and this guy's just sitting around twiddling its thumbs. Twiddling his thumbs in the sense of calling run IO, calling run IO, calling run IO. But hopefully that should be relatively uniform. And if we're using the IP address and port, there's no reason to think that that shouldn't be relatively random. If we suddenly start getting into, let's say, 40 gigabytes per second, if we start getting into 40 gigabits per second, that can stress the amount that we can actually handle in RAM. So copying the data that is incoming or copying the outgoing data actually might be too much that we can't afford to do that. So instead, what IX does, it uses the page table, it maps the packet buffers. So the packet buffers, so they're in the IX kernel and the app memory space. The ones for incoming packets are read-only to the application. So the application can't mess with the incoming packets in any way. Once it calls run IO, it gets told where the data is and it can then read from it and decide what the correct response is. So run IO has pointers into these packet buffers. So the application will use one of these buffers when it's writing its outgoing data, and in run IO then provide pointers to it. When you call run IO and there's an incoming packet, it'll be put in one of these buffers, and that comes back in to via run IO to the application. When the application is done with it, that's one of the things it provides back to run IO to say it's done. And then the kernel, IX kernel, can reuse it. The design here works great for its intended situation. That is, many parallel clients making small requests. And not only making small requests, but making small requests that tend to take about the same time and that don't require waiting, like waiting for disk or something else. If you had just a single 40 megabits per second transfer that you were trying to do, this wouldn't be the approach that you would want to use, right? We're taking advantage of the fact that we can easily segment the data into multiple completely independent. That wouldn't be the case if you had a single TCP IP connection that you were trying to blast as much data through as fast as possible. It also assumes good load balancing. Okay? It assumes that you have roughly balanced queues. If they weren't, it'd be kind of hard to tell what to do. Reassigning the flows would be kind of difficult. I guess you could somehow, it would be very difficult to reassign a connection that was currently running. You can imagine new connections could go from one queue to another queue, let's say, but it'd be hard to sort of take a flow as it was going because you'd have to copy all of the TCP IP connection information over. So that would be information. That'd be difficult. Is there any way you could steal work? It's unclear. The whole point of this is the way it's designed is they're completely independent. So it's very hard if you suddenly start to make them dependent on one another. It also assumes this non-blocking request handling. That is, that the application can read a request, do some sort of computation, and then provide a reply. Doesn't read the disk, doesn't send an RPC somewhere else and wait. Blocking would be a problem. We'd have an idle core, our queue would be expanding. That's not how this was intended.